Welcome back to the New Stack Agents, our show about all things AI and agents. Today we've got Alex Williams again, founder of the New Stack, and our guest today is Naveen Rao, VP of AI for Databricks. Naveen, thanks for being here.
Thanks for having me. Excited to
Absolutely.
for the discussion.
Now, in the pre-show, we just talked about the first computers we all had, and it's such a trite topic to some degree, but yours are really interesting because you're pointing out some of the stuff you got in the background there. But what was your first computer? How did you get started in this?
So my dad, who's a physician, but just always loved gadgets. I mean, we had, ham radios and all kinds of stuff like that. So yeah, I guess my brother kind of got that bug and bought a Texas Instruments 99 4A in 1978.
Wow.
And yeah, he used to do some stuff with that. My brother's 7 years older than me, and so I learned to code first in Logo, if anyone remembers that language. You have a mouse or a turtle, I think they call it.
The turtle.
Yeah.
That was the thing. Yeah.
So I learned, you can do like for loops and all that kind of stuff in that, and you can draw games and everything with it. So I learned that first, and then I started to do basic programming. So that was like when I was 8, 9, something like that. So back then it was such an esoteric thing. No one even knew what a computer was, right? But yeah, it was just a weird curiosity, I guess.
Now, the one thing we want to talk about is how you went from that curiosity to working on biomimicry and computational neurobiology, and then deep learning and large language models and all those things. But kind of how did you get started in the industry?
In AI?
Yeah, or in general, really.
Yeah, I mean, I think I've always been into building stuff for whatever reason. I'm just wired that way. I mean, I see it with my second son is the same way. Like, you can't really stop people from building stuff, even if they have that mentality. Like I started building circuits and things when I was in 5th, 6th grade. I remember building like a buzzer system for our quiz bowl type team. So I built out a logic chips for Radio Shack. So that kind of stuff was fun. I actually would draw the circuits out on a computer first, and figure out if it's going to work. So I don't really know where that comes from, to be honest with you, but there's just something interesting and exciting about a circuit that has memory, or something that can do math. Like, I don't know why that was fascinating. And of course, you just end up reading a lot of like sci-fi and things like this, so you fantasize about what could be, and sometimes that leads to careers, I guess.
Yeah, no, Alex.
Yeah, I'm just curious, and that takes you to, I think, around 2012, when you said in an interview I saw that you did with NTT about the real arrival of deep learning. And what strikes you about that time that's so distinctive?
Yeah. Well, I think actually you got to back up a little bit to give context. So, again, having this idea in your head that you could build a machine that's intelligent, I think that concept was just mind-blowing to me, even as an undergrad. So I studied AI as an undergrad. It's like 1995, 96 timeframe. And, it was sort of more creative algorithms. How can we learn? What does learning really mean? And so there were many definitions then. And I would say that, the kind of more regression methods started to dominate. So neural networks actually had a thing in the early 90s, right? So that's when Jan LeCun and Linnet and all that stuff happened. Yeah. Actually had some early success with the post office reading digits. And there's something from Terminator 2, one of the biggest movies of like 1991, 1992, where he said, I have a learning neural net processor, in his head, which I thought that was actually, it kind of foreshadows where the world was going. But then the support vector machine by Vapnik et al. Kind of killed that, because much easier to train. It works in a lower data regime, which computers weren't really ready yet from a storage and processing standpoint to deal with lots and lots of data. So regression methods work pretty well, and it's easier to train, computationally efficient, all that. So it kind of killed that research. This is a history that you can read anywhere, but a small dedicated set of people were continuing with the neural network stuff. And it wasn't until the mid 2000s that you started to see a place where the data regime became bigger. Like, now I had more examples to train off of, and it started to saturate the performance of these regression methods. We added things like ridge regression and all kinds of tricks and gradient boosting and stuff like that. But actually, what you started to see was like, now you're looking for something that's almost model free, that can learn the model of the data from the data. And that's where neural networks started to do something interesting. So if you recall, like way back in the recesses of your mind, we called it feature engineering. We would engineer features of the data and say, these are important combinations of the data. And neural networks could discover those features automatically just through iterative learning. Huge shift, right? And then 2012, I think, was an inflection point where I would say 2005, 2006, a lot of the academic work started, and all of a sudden it just destroyed the regression methods in something which is a kind of a quantifiable benchmark, the ImageNet. And so that's when we saw this enormous leap that all of a sudden became very close to human performance, which we'd never been anywhere close to that, except for maybe Deep Blue in the late 90s. So I think that's why I see that as like an inflection point in this whole industry. Like 2012 was the date that all of a sudden people started thinking, wait, the future of compute might actually be neural networks.
And you also mentioned in one of your talks about the brain and how it runs on 20 watts, I believe.
Yeah.
And you also talked about, hardware and how far it has to go in terms of its development.
Yep.
There's an interesting corollary there between the 20-watt brain and gigawatt data centers. And I'm curious what that means to you.
Yeah, I mean, that 20-watt information I learned when I was in undergrad. And it's something that, and also that the fact that the retina does a real-time Laplacian before it sends the data back. It's like a transform that does to the data before it sends the data back to your brain. It was just kind of amazing that you can see these computations occur in biologically evolved systems. So these things that through undirected evolution kind of came up with these concepts, which is pretty cool. But at the same time, was constrained by energy, always. Everything in biology is always constrained by energy. You can only eat so much, right? And the advantage that's gained has to give you an advantage in finding food and survival. So, our brains both became more complex and the ability to do a lot more computation, but also became extremely efficient. So fast forward to where we are now. I mean, we've kind of built the same computer for 60 years in my mind. I mean, yeah, GPUs are different. Okay, fine. They have more computing elements, but they're sort of the same thing. You've got like an ALU, right? You've got a memory interface. You've got caches. It's like the same basic machine. The parts are a little bit, different in the way they're arranged. A lot of the differences really come from the fact that we can jam so many transistors into a package now, and we can put a lot of energy into that. I mean, the latest GPUs are 1,000 watts, the new ones are going to be a few thousand watts. Just to put that into perspective for people, these CMOS silicon logic chips run on about 0.9 volts. So if you're at 1,000 watts, you're doing 1,100 amps. Like your car, you have an internal combustion engine car, it's turning over with 70 amps, 80 amps. So this is just incredible. In a package about that big, you're jamming that much power in. So I don't actually think this is the right way to go if I want to use biology as kind of a guide. So to your point here, like we brute forced our way to some sort of intelligence now, and it's amazing. And we always do that. That's how technology gets developed. But my personal take is that, these gigawatt and 100 gigawatt data centers or terawatt data centers people are going to talk about in a few years is the wrong path. It's not going to get us there. We need to build something that's fundamentally more efficient, fundamentally, more well aligned with what AI is, how AI represents information. Like there's something we're missing here in terms of computing elements in my mind. I can't say what that is yet, but
I was just going to ask you, what do you think that is? But even if you have to like, how close do you think we get to? It all depends on definitions to some degree, but to real intelligence with the approach that we have right now, or would you almost argue with there already?
I mean, close. I think, I would argue a mouse has real intelligence. So can we get to a mouse intelligence? Maybe. I think we'll be able to brute force our way conceptually to get pretty far. I think what happens though is we're taking this approach of like just throw more at it, and one, it won't be economically viable. That's for sure. But I think the other part of it is that it'll be very limited in what that AI can experience. The low power aspects of biology enabled intelligence to experience more. It's like a parallelization. When I have more creatures with brains experiencing the world from different perspectives, I'm gathering that much more data. I'm learning, and then somehow the genes do actually learn and pass that on. Like there's this, life is a learning machine with many different like observational points. I don't think, gathering data from one set of sensors or the internet and then jamming it into a data center is actually the right way to do it. So, yeah.
Cool. Yeah, we've gone through these cycles, right? This is another one of these cycles where we'll figure out. We'll probably hit some plateau at some point, and then figure out.
I think we've already hit plateaus on the current paradigm. To be honest with you,
that's a statement for sure. So you think the next generation of models won't improve by that much anymore compared to what we have?
I would argue that they're not improving by that much. They become more useful. I mean, it depends on how, I'll get pushback from anyone when I say that, because they're like, no, look at how much better they are. It's like, yeah, sure, they're better at particular things because now we know what we want to use them for. They're super useful artifacts. I'm not suggesting they're not useful, extremely economically valuable. And of course, that's what I do all day, right? I make these usable for people. So I think they're very useful. They have a lot of economic value, but at the same time, are they building super intelligence? I actually don't think so. I think we've been able to push the distributions around. We can now use reinforcement learning to make them better at tasks that we care about, but they still make very dumb errors, and that's partially because of the way they work. And they don't have some sort of notion of a reality. Like they basically take observational data and then form some latent representation. That latent representation, by definition, will always be incomplete because I can never observe the whole world.
Right. Well, you said the superintelligence word, and while we're recording today, Mark Zuckerberg had his post about personal superintelligence out, and I don't want to go into the depth there, but his first line I thought was interesting, where he talks about that he's seen glimpses of their AI systems improving themselves, right? So I think that's interesting because that's something people have talked about for a while. Like, what's your take there? Is that something you're seeing as well?
Yeah, absolutely. In fact, our team published something called Tau, which is a way that you can kind of iteratively self-improve through an automated reinforcement learning, no labels required. So I think, we and others are working on ways to do this. And if you think about it, it's actually sort of similar to that moment in 2012 where we went from like hand-tuned features to learned features. Then now we're in this realm of, okay, I need to judge whether a data point is good or an output is good. So can I learn that judgment? And so it's basically continuing along the line of, can I automate the thing that I'm getting, that I'm trying to optimize? And I think the answer is yes. So yes, we will iteratively make these systems better. And will that make it super intelligence? Maybe. I think it's a big maybe still in my mind.
Okay, fair. Let me get back to your story a little bit too, because then you found Nirvana as your first AI startup, really. Kind of what was that all about, and what did you think this was all going to look like back then when you started the company?
Honestly, I think it went exactly what we thought it was going to go. Like, nothing is a surprise to me from an infrastructure standpoint. Which, I don't know, maybe that sounds like not a very humble statement to make, but we knew this was going to happen. This was not a surprise. So I was a researcher at Qualcomm, which Qualcomm actually had a really good AI research team back then, arguably one of the best, maybe second to Google. And we were trying to come up with ways that we could use spiking neural networks, like neuromorphic computing, things like this. And that was around 2011, 2012 when I joined. And so kind of coincided with this ImageNet moment. And obviously we were keeping tabs on that. And I started to see, like, okay, now we can start to describe real solutions, real ways of iteratively getting to a better result with neural networks, and it works in practice. So this is a new way to describe what a computer does. And so I had just finished my PhD a couple of years prior to that, and basically the whole goal of my PhD was, I had been a computer architect for 10 years. I designed multiple chips, kind of knew how a computer worked. And I wanted to go back and understand what we know about the brain. And are there things that we can harvest, knowledge that we can harvest to build better computers? Really, that was my goal. And at that time, this was 2007 when I did that, it wasn't really clear if this was going to work, and nobody cared, you know. But by this time now, I said, well, this might be the moment. And so we actually founded the first AI chip company, which was Nirvana. And really, it was, let's build a processor that's designed explicitly for neural network compute from the get-go. And what does that mean? Well, it does, you know, lower precision matrix multiplication very, very well, cheaply, and energy efficiently. It does scale very, very well. So the first iteration, the first version of this chip was actually a highly distributed processor. Like, the programming model for one chip or n chips was identical. And so, I mean, now we're talking about putting 100,000 or 1 million chips together. I mean, this is, again, not a surprise. We built a mesh architecture to be able to do this. And so this was in 2014, and, you know, infrastructure is hard. It takes a long time, as you know. So the world kind of went in that direction after the algorithms got up.
And you went to Intel. Nirvana sold to Intel. Was that the right move?
No. I could say unequivocally that was not the right move.
Explain.
Well, okay. At the time, you have to keep in mind, you know, founders are people too, and we all have lives. I quit my job in 2007. My family thought I was crazy. I had 1.5 kids, and I went through a divorce, and I was in grad school for 4 years. So monetarily, not the best decision. Right? it's just, let's just be realistic. I was in Silicon Valley, and, you know, made pretty good money, and then I didn't have a salary for 4 years. So that presented some economic challenges, and, you know, I burned through a lot of savings through that. And then when I started a company, that was also met with some resistance, we'll say, because it's like, wow, that's really risky. Why are you doing that after you just, you know, spent 4 years, you know, not making any money? So life happens, and all of a sudden there's this offer that was bigger than I had seen, and bigger than most people had seen at that time. $400 million was a lot for a company then. And takes all that pain away, right? My kids' college education was paid for, and all that. So I would say the decision to do it was somewhat out of fear. I was also scared about the market. Like, at this time, it was 2016. I think we were on a bull run from about 2011. So we've been on a 4 or 5 year bull run in the markets. And I was like, oh, are they going to pull back? Like, what's going to happen with investment? Am I going to be able to raise money? You know, building chips is expensive. So I overcalled the risks because I was scared. I'll be really honest. And there were a couple of places we could have gone, actually, at that time. Intel, I didn't actually know about all the woes that were going on the inside, but really the thesis was simple. We have the best architecture. They have the best process node. Let's put them together and build the best possible AI chip.
Yeah. And then the process node started, you know, not being the best anymore. And that's where Intel is where it is today. Did you see that? You know, we know, everybody knows where Intel stands today, but did you see that coming while you were still there? Because you left in 2020, if I remember it right.
I did, yeah. No, I definitely saw it. In fact, we had the Nirvana chip. So it was very strange, actually, when we came into Intel. I can go through the story quickly, but it was a bit of a political battle between a few different folks inside the company.
Political battles at Intel? No.
I know, right? Such a foreign concept. But the whole acquisition itself was driven by some political battle. And so it was not even agreed upon inside the company that deep learning was important. So there was Xeon Phi, and everyone's like, oh, this is a fad. You don't need to do that. HPC is where the future is. So a lot of people didn't want us to even build the chip. So the first chip, we hadn't taped out yet. Taping out means the design is complete. We didn't tape out the chip yet when we got acquired. And, you know, we were actually raising money when the acquisition happened to scale up the team. When we came into Intel, we got put under a hiring freeze. This was just after a big layoff at Intel. So it was like, guys, we can't get the chip done. So it was a very small team. I'm going to say 15 people who worked their asses off to get that chip done. And they got it done. Amazingly enough, we taped it out, chip worked. But it was late because we were going very slow at that point. So it wasn't until like the summer of 2017 that we actually we formed this new AI group and got funding to move forward. And that's when we could kind of start making the effort go. Now we said, okay, let's make the next rev. Let's do all the new things we've learned. And we started to build on Intel process. We wanted 10 nanometer. That was the new cool process. I started getting these weird signals like, well, maybe you want to think about not doing that. Why just on 14? So, okay, fine. So we'll go on 14 and we'll move to 10 quickly after. So about a year into development, so I'm going to say beginning of 2018 timeframe, we started to see the chinks in the armor. So if you look at the headlines, you can start to see there were some things leaking out at that time. It was a total shit show. And we said, oh man, we're going to have to change. So we actually scrapped the design, restarted it to work on TSMC 16. And so that was yet another delay. So we burned 2 years at this point, just screwing around, right? Like literally didn't get anything done. That chip did eventually come out and work in the summer of 2018, or maybe late summer. And we did ship it to some customers, but now we had to rethink it, and we weren't going to use Intel process. We were going to redo this. And actually we came up with something that was pretty cool. We were going to fab wafers in TSMC, but package them in Intel, which was, I think it's still pretty cool. That did actually end up happening. But it was unprecedented. So you're breaking new ground. And then, Intel got so defocused. If you remember, this is when BK got ousted in summer of 2018. He was my boss. Yet another set of political battles. And, it was just this political hit job. People wanted to take me out. I don't know why. I was like, I just want to build. I don't care about your politics. I don't care about my title. I just want to build this thing, guys. I'm still mad about it.
Intel likes to build little fiefdoms.
But there's always tomorrow, right?
We move on, of course, but I still cared.
Yeah, and that's what it's about, right? You just keep building, right?
You do.
And that reminds me of what you said also about thinking through rebuilding the physical substrate of chips. I'm curious about what you mean by that. And you also talked about we live in a world of zeros and ones, but there's other numbers out there too.
That's right.
And I'd like to get your explanation of that and what you mean.
Yeah, when I say we built the same kind of computer for 60 years, it's zeros and ones. It's synchronous design, meaning that there's a clock signal that kind of times everything together. There are, finite bit width representations of numbers. We have 32-bit floating point or 16-bit floating point. And floating points, floating point standards were defined in the 70s. So these are not new things. We're just kind of rehashing, moving the transistors around and packing them together tighter, right? That's really what we've done. We've not changed anything conceptually in a computer for a very long time. In fact, I was just having a conversation with someone pretty prominent. I won't say who on this publicly, but we started talking about what is relevant? I pulled up my Patterson and Hennessy book. That's why it's sitting next to me. This is from 1995. I took computer architecture as an undergrad. So I kind of flipped through it. Still the same stuff. You can read that. You can understand what's happening in a GPU, no problem. The field hasn't changed that much. So to me, we kind of have entered this regime of, I'm just going to try scaling along some dimension. I scale along power, I scale along device size. Device size doesn't scale anymore. Okay, well, I'm going to jam more in with packaging and I'm going to put more power into it. Okay, that's fine. But what we need is ways to represent information more flexibly. Potentially trading off time for accuracy, for power. We don't have that capability really in a system. There have been these concepts out there. There's things like the Landauer limit, which is theoretical limits of minimum power of computation. These have not been explored for a very long time, and largely because Moore's law worked. It works exceedingly well, and there was tons of economic value to just continually making the devices smaller until it stopped, right? So we're at this point where maybe, we have the use case. Intelligence is important. We got it. Everyone gets that now. We know it's going to be consumed en masse. People are already doing that. And we know that economics are going to be important. So I think the factors are coming together again to start opening that back up, maybe building a new machine.
Yeah, and we've already seen the impact on software development with AI. I'm curious about your work at Databricks and how you're seeing that in your own work and how AI is changing your view on software development and how that relates to what you're saying about hardware improvements and changes that are needed.
Yeah, I mean, certainly at Databricks, we're employing all the latest stuff. I mean, we started, we had Copilot pretty early on. We rolled it out to the whole company. Cursor. We work closely with Anthropic and all the model providers. So yeah, we're using it all throughout. This is an important thing for us to make sure that we're on that bleeding edge of the best tools so our developers can go fast. Now, in the software world, you tend to do somewhat similar tasks over and over again. And that's where these tools, they really shine. Like, I don't need to think about templates. I can tell it what to do. I don't need to think about, headers and project structures. All that stuff ends up being very similar each time you do something. And so that boilerplate stuff can be automated, which is great. And it just makes everybody more efficient. When you're designing a chip from scratch, you do a lot of that as well. In fact, I would even argue more for a chip, like defining interfaces and stuff. That's in the sort of digital logic design flow. So I think there's a huge potential for AI to make that faster, make it closer to bug-free, like speed up development and verification cycles. I think there's a huge opportunity there. But thinking about new devices, new physics, the way we build this stuff to use it in new ways, represent information in new ways, I don't think AI is going to help you there. And this is actually something fundamental. What we call it in the field is being out of distribution versus in distribution. If a set of ideas are within the training data, yeah, it's really easy to flexibly call them up and apply them in new situations. When ideas are brand new, I haven't seen AI really give me something new. Like, can it really do a PhD thesis? Like, this is actually, most people don't know this, a PhD is literally addition of knowledge to humanity. That's the bar for getting a PhD, or is it supposed to be? So I remember seeing this graphic years ago where it's like, as undergrad, you learn this is what most people in your field know, and then as a master's, you learn make that a little bit bigger. Then you learn the edge of human knowledge, and you pop it out a little bit, and that is a PhD. You make that circle just a little bit bigger, right? I don't see LLMs doing that just yet.
I'm just thinking, when just a few years ago at Databricks, you built your own LLMs, right? I think it might even have been last year, right? Was that kind of an effort to do that kind of work to make LLMs just a tiny bit better at the time? And you kind of stopped doing that, I think, at this point. But
yeah, I mean,
what was the reasoning?
Well, so at Mosaic, before the acquisition and then through the first year, we were very focused on the economics of large language models. How do we make them cheaper to train, more accessible, and cheaper to serve? And if you recall, that was actually the first large-scale mixture of experts architecture, which was very efficient. In fact, it was the most efficient at the time. And now everything is an MOE because it is more efficient. So our idea was really to continually push that Pareto frontier of, intelligence per dollar. That was the idea. And what we deemed our strategy was going to be costly to keep doing the model wars. And then we said, Meta is going to invest heavily in this and do it for everybody, for the community writ large. So we said, why don't we just pair up with them and work closely? And so the Llama models, we worked with them quite a lot, which was great. I think a fantastic collaboration. And I think that's going to continue. Like we're looking forward to seeing what the new lab, superintelligence lab, comes up with, and we're going to continue to give feedback and tell them what we think we need for enterprise. But at the same time, we are still doing pretty fundamental research on how we can do reinforcement learning at scale with customer data.
Sure. What you haven't gotten an offer yet from Mark to join the superintelligence lab?
I have not.
Good to know. Now, the one thing, you talked a lot about hardware, right? And your background is in hardware. Obviously, that's not what you're doing right now to some degree. Like, where, are you thinking about that again, or is it something? Because Databricks is obviously not going to be interested in doing hardware, I would think. But
I'm focused on our customers' problems at the moment. But yeah, an AI hardware is pretty intrinsically tied to what you can do algorithmically. So every iteration of deep learning has the fingerprints of the architecture of the hardware in which it was built. So this is actually one of the moats that NVIDIA has had, is that people build on NVIDIA, and that actually changes. It makes decisions on how you build the architecture of the neural network, because of the architecture of the chip. So they're so much more intrinsically tied than other workloads are. So I think if you're in the system side of AI, which is frankly one of the most important, because you have to make it run in a reasonable amount of time. Like if you're on the system side, you are never that far away from hardware.
That connects the dots about the UI, and when you talk about the UI, doesn't it? And that developer experience as well.
Yeah, absolutely. And so that was a set of observations that, okay, now you have this magic new capability. LLMs that are super high quality can do lots of things, but if you really want to get consumption of these things, you have to think about reduction of friction to delivery of those capabilities. And we don't deliver all computation, as like a calculator, right? I almost think it's like a chatbot is like a calculator is to the original computers. Like that was the first thing we did, was like automate. There used to be humans called calculators, right, who literally would do calculations for scientists. Then we automated that, and we made it, you type it in. But then computers took on a whole new meaning once we started doing like Excel and all the apps that became the ones that you know and love or hate. and I think that's where the value really exploded. It was like we figured out how people are really going to consume computation, and so that's kind of the cycle we're in right now with LLMs.
Alex, I know you wanted to talk about copy and paste. I think this is the point where you should bring that up.
Oh yeah, I love this idea of how copy and paste is the ultimate example of how AI does change the work experience.
Yeah.
In many ways. And I think it's almost like a metaphor for a lot of things. I mean, at your conference, the Databricks conference, you discussed Neon and the use of agentic AI.
Yep.
And how Neon, is one of those technologies that makes you think differently about the relational database.
That's right.
And it seems like these things are all interrelated. And I'm wondering if you think through that a lot in terms of, yes, it's cut and paste, but it's also a lot of other things, such as, the corollary to agentic AI.
Yeah, I think what's really interesting now is, and this is true for UIs, it's true for everything, is that AI is different from everyone's mental model of how software worked. So, before it would be like, okay, well, I can build a piece of software to solve some problem. It's a static thing. And then I can say, oh, well, there's some modular components of that I may be able to reuse and combine in new ways, and then do that again for another problem. And so we get libraries and OSs and all that kind of good stuff. But each one of those components are static. They're always going to behave the same way, and unless you change them. With AI, and so it goes back to this idea of like iteratively learning. The systems are not static. They can learn from their usage. And I think that's what we're trying to work toward, is this agent, which you tell it what to do, you can give it task descriptions, but it can continually improve as it's being used. The loop today with software development is I develop a static piece of software, I make it a SaaS or I sell it or whatever. I observe my users and their complaints and their usage patterns, and then I feed that back to a product manager. They come up with new features, we iterate, we change the software, we roll it back out. That's the loop. We release software every few months or year or whatever. So that loop can now be tightened. That can be automated. That feedback loop between how it's being used, how the value is being delivered can be tightened and improved and made faster and faster and faster. Few people are contemplating that. And I think when you think through an AI strategy, that's actually very important. How do I use iteration to improve something and make it more valuable?
What's the end result of that? Is it just faster software releases though, or what else is there to it?
AI, you can almost think of as the software is almost like a context. It's continually evolving, right? So it's not a release. It just gets better. It's almost like a person, right? You don't think of a person as you're not released, July 30th, and then tomorrow will be, July 31st. You think about it as, every one of us would probably say we're a different human from what we were 10 years ago, right? But it happened through a continuous evolution.
Until we get that neural link installed and then we get the firmware upgrades.
Yeah, I suppose. We'll see.
Or faster if AI.
It's actually what I worked on in my PhD was neural interfaces.
Oh, really? That's interesting. Do you think that's coming back? Actually, since you brought it up, is that kind of something that's going to come back?
Well, Neuralink is going after it, right? And
sure, but
making a lot of statements about it, but it's a very, very hard problem when you're trying to interface with biology. So I think it takes a while to build the right materials, technologies, and things to make that stable. So, you can use it where somebody is injured and they have no other choice, but to make it something that's a consumer item is going to be a while.
Yeah, for sure. Let me bring us back to data for a moment, if that's okay. Alex brought up Neon there, for example, and I'm wondering how you're thinking about developing right now when the customer, the user becomes an agent, right? How does that change how, not just software is developed, but how software interacts with other software, how humans interact with it, how we build it when the consumer is the agent?
Yeah, monitoring starts to become extremely important. You make sure these systems are doing what they're intended to do. I think humans are still, at least for now, the ones in charge of the intent. What is the system meant to do? And I think humans move into more of an oversight function over time. Monitoring these things, using deterministic software actually to parse through some of that and say, is it doing what we expected it to do, right? So I think that's something that we see that's going to be important, and we're building toward that future. Obviously, making all tools friendly and amenable to being to consuming output from an LLM. So that's what the OLTP stuff and Neon, Lake-based, that's what it's about, is can agents spin these things up with a purpose? And when they do things wrong, also you have to be able to deal with that. So I think there is some difference to when you build for consumption by an agent versus consumption by a human. You can make some assumptions about a human, maybe you can't make with an agent. So these are the things to think about when you're changing your direction to be consumed by AI.
How would we theoretically lose that oversight of AI? How would that happen? And what would be some theoretical outcomes of that?
Well, I think, it could have happened, let's call it a year and a half ago, before we had any kind of governance or permissioning tools, right? It was a bit of the Wild West then. You could say, here's a function call and it just does some stuff. Now we and others have built these more clear governance structures where, I'm going to call a function from an LLM. That function has certain bounds of what it can and cannot do, and certain data that it can read or can modify. All of that has to be tracked, and there has to be a lineage associated with it. So you have to be much more explicit about what the model can and cannot do. So I think that's how we prevent anything going off the rails. is that we just lock it down and put the appropriate controls around it. The scenario where something bad happens, I mean, there's always going to be bad actors in the world, but I think within a company, if they learn the proper practices, which I actually think that a lot of big enterprises are doing that now, especially with tools like Databricks, they're seeing the importance of like, wait, now we need a centralized governance structure. We need to explicitly say what these agents are doing. You know, if I have a customer support agent, like it shouldn't have access to HR data, for instance, or marketing data, or it shouldn't be able to like change something on the website. Like these are very clear boundaries that these things have to have. So just being really clear about that. And that becomes like actually a proper schema. You know, it's not something that's probabilistic in any way. So answer your question, how does it go off the rails? Well, I think if you don't do that, you start to have unfettered access. I think we're already entering a regime now where I think more of the content on the internet will be machine produced rather than human produced. It's already happening. I would probably say we crossed that point of more than 50% is machine produced. So a bad scenario of this is something we call model collapse. Have you ever heard that before? It's basically that LLMs are continuing to scrape this stuff, train on it, and then learn stupid stuff that other LLMs spit out rather than a real ground truth of the world. That's a real proper scenario that is going to happen very, very soon. What results from that? I don't know, honestly. Like I think this hallucination problem could potentially get worse, or it could get more and more complicated to detect because maybe even your evaluation data sets have some of these non-grounded facts in them. So I think grounding things to some sort of reality is actually important. And at Databricks, we've taken the tack of let's leverage what people have built for data. We have this medallion architecture where we talk about like, bronze, silver, gold data that's been cleaned and, determined to be as true as possible. That's not just relevant now. It's extremely important.
Yeah, that's why the models need to learn from our content and not from the LLM produced content.
That's right.
But now I'm always interested, how many agents do you use yourself, or either personally or in your work, or are you doing any of that yourself at this point?
I mean, coding agents, I've definitely played around a lot with those. I would say that's the vast majority of it. I use things like ways to clean up writing. If I have to write, many times I take notes just in notes, and it's kind of like I jot stuff down and I get it to format things. Those sorts of things, that's pretty standard stuff these days. I think in like in email and Gmail, everyone probably uses some of this now where, did you want to include this other person? Like, did you want to include that document? Like it starts to pick up on all these things. And so I think that's actually, it's almost an insidious use because it just happened in the background, right? You don't. Right. So I would say that's probably, if I really thought like where my tokens that I consume are coming from, I would say coding and probably email is the biggest one.
I think that's probably true for most of us.
Yeah, I don't do a lot of image generation or video generation stuff. I mean, I don't know. Maybe I'm just too old for that at this point.
You should try it. VO3 is definitely fun too.
It is fun. No, I've totally done it. And then like,
not sure what to do with it. Like,
stupid stuff with my kids.
No, it really amuses my nieces though, so I'm all for that.
Oh yeah, no, totally. I see that.
Keep the kids occupied. But hey, thank you so much for being with us today. Really appreciate it.
Absolutely.
Great conversation. Appreciate
Thanks,
it,
Naveen.
Alex.
Yeah,
thank you as always. We're going to take a break next week. I'm going to be going on vacation, so break next week, and then we'll be back on August 13th with Scott Carey from LeadDev to talk a little bit more about agents and
what
developers.
The data says.
Yeah, exactly. Yeah. Yep. So that will be fun. We'll be talking about a report about all of that good stuff. So awesome. Thank you both.
Thank you.
Thank you.
Thanks, everyone.